So now that we're pretty good at driving off cliffs, let's talk about going in circles. Okay, so this is going to require a little bit of new information because remember, if you're going in circles, is X and Y coordinates a good way to describe circles? So like if you want an equation for a circle in X and Y, what do you have to do? It ends up being like x squared plus y squared is equal to something that's like the square of the radius. It's a pain, right? But the other thing we want to remember is if it's uniform circular motion, what does uniform motion mean? Constant. Constant what? Speed. Constant speed. That's what we've been talking about in terms of uniform in this class. So if we take this snapshot graph where we take a picture of where this is at equal intervals and we draw out our velocities, right? You can see all of these arrows are about the same size. Okay, so they all have the same speed, but what do they not have?
Same direction.
Same direction. And what does changing direction tell us about acceleration, for instance? So we're not changing speed, but we are changing direction. Do we have acceleration? Right, we do. Which way would that acceleration point? Towards the middle, yeah. So in order to talk about this, we're going to have to define a couple new terms. This is the less exciting part, but we'll start with period. And period is the time it takes to go around a circle one time. Okay? So one revolution, this is the time. Okay? Frequency is just the inverse of period, so it's the number of revolutions per second or per time. So if like like the unit RPM, right? That's rotations or revolutions per minute. Okay, so period and frequency are related. Frequency is just 1 over the period. Even though RPMs is a nice unit, what we really want to do is seconds. So whenever we're doing problems in physics, we convert everything to seconds essentially. So periods in seconds, frequencies in seconds. Okay, and then speed for circular motion. Well, let's say you have a circle. What is the distance around a circle? How do you figure out the circumference of a circle? 2 pi r, right? So that would be your distance of the circle, right? And what would your time be to go around a circle once? The period. Right? That's the definition of period. So if we know the distance and we know the time, what can we calculate? Speed, right? So the speed for circular motion is just 2 pi r over period. And because we know it's uniform, we can calculate speed this way because we know it's not changing. Okay, so distance over time works. We don't have to use the derivative because the derivative is the same as this ratio as long as it's constant. So it's 2 pi r over 2 pi r over period. You can also write that as 2 pi r times frequency because we know frequency is 1 over period and vice versa. So these are our definitions of the things we're going to need to get started. Okay? So remember, period is the time it takes to go around a circle once. Frequency is the inverse of period. And speed for uniform circular motion, not all circular motion, because sometimes things move in a circle and they can speed up and slow down. That's a different set of parameters, but we're going to start with this simple model just to get the idea of how the acceleration works. Okay? Cool. We're going to do a problem together, and just give me a second as I screen share. I think it's a little easier the second time. Okay. So, somewhere. There we go. So let's talk about uniform circular motion. So we have, does anybody still have audio CDs? I'm gonna have to like update this problem to, yeah? Okay. You guys are all aware that some people in the past played music with these round discs? Yeah? Okay. Oh, yeah. So we could just make it vinyl. That's easier. They don't spin as fast. Okay, so an audio CD has a diameter of 120 millimeters and spins at 540 RPMs. Remember, RPM stands for rotations per minute, so you can write it as like revolutions or rotations divided by minutes. When a CD is spinning at its maximum rate, how much time is required for one revolution? And then if a speck of dust rides on the outside edge of the disk, how fast is it moving? Okay, so mostly what we're doing here is conversions, because we know that we have some values. So we have, what's 120 going to give us?
60.
Yeah, we want a radius of 60. So we'll say radius is equal to 60 millimeters, but what do we really want things to be in? Meters. So what does that look like in meters? 0.06 meters, okay? Because 60 millimeters is 6 centimeters, and that's 0.06 meters, okay? Next, we have this 540 RPM. Is that frequency, a period? What is that? Yeah, so the frequency is 540 revolutions per minute. That's probably not how we want to keep that. So the first thing we might want to do is convert frequency. We use our little ladder method. So remember, frequency, we're going to say that's 540 revolutions per minute. But we want this in seconds, okay? So how many seconds are in a minute? 60. So that means we have 1 minute is 60 seconds. So really we're just multiplying by 1. Then we cancel things like minutes. And that's going to give us 9.0 revolutions per second. Turns out that revolutions is kind of a weird unit. It just goes away. We could just call this 1 over seconds, okay? And the other thing that we want to know about 1 over seconds, there's another word for inverse seconds, and it's hertz. So this is, you can write this as 9.0 seconds inverse, or you can write it as 9.0 hertz. Okay? That's frequency. Then if we want to find period, how do we find period? We have frequency. What do we do with that? I can wait. Yeah, so just take the inverse, right? So 1 over frequency, that's going to be 1 over 9.0 inverse seconds, or hertz. And that's going to give us 0.11 seconds, okay? Last but not least, we want to calculate the speed. So what's our speed going to be? Well, remember, from the equation, it's 2 pi r divided by period, or 2 pi r times frequency. Those are the same thing. So we say 2 pi, the radius is 0.06 meters, and then the frequency is 9.0 hertz, or inverse seconds. Plugging all that stuff in, we get 3.4 meters per second. So we have now our 3 answers. Our frequency is 9 hertz, our period is 0.11 seconds, and our speed is 3.4 meters per second. Okay? So we're just getting used to using these new ideas about rotation. Let me see. What's next? Okay. So this is our answer. And then let's talk about the acceleration. So we sort of assumed that this points towards the center. And just to visually look at what that means, that an acceleration that always points directly towards the center of the circle is called centripetal acceleration, not to be confused with centrifugal acceleration, which is a slightly different thing that we'll talk about later, and also a fictitious force, which sounds a lot more whimsical than it is. It's really just the force you feel versus the force that's actually driving the system. But an interesting thing about centripetal acceleration, which I would also call radial acceleration, because we're going to define some new coordinate systems that work better for circular motion. So everything's going to be broken down into radial and tangential. What do we know about coordinate systems? What do the different variables have to be to each other? If we're going to break things down into x and y, how are x and y related to each other? Yeah, they're perpendicular. So remember, if something's pointed towards the center of the circle or tangent to the circle, what are those things? Those are always perpendicular. So radial vectors and tangential vectors will always be perpendicular to each other. Something tangent to a circle is always perpendicular to something radial. Okay, so pointing towards the center of a circle. So we can see that all of these velocity vectors are tangential vectors. All of these acceleration vectors point towards the center of the circle. We'll call that radial vectors. So we could write this as radial acceleration, meaning, so sometimes we were talking about acceleration in the x direction, acceleration in the y direction. In this case, we have acceleration in the radial direction. Do we have acceleration in the tangential direction? No. What would happen if we had acceleration in the tangential direction? What would happen to the velocity vectors? They could, yeah, they might point outward, but they could also get bigger or smaller, right? So they could change direction, and they could also get larger or smaller, because if we had an acceleration vector that pointed this way too, that means these would be getting bigger. If the acceleration vector pointed this way, these would be getting smaller, okay? So those are all different ways. So as long as the acceleration vector stays constant and points towards the center, the circle's not going to change size. What if the acceleration vector changes over time? What if it gets bigger towards the center? What would happen to the motion? So if it starts accelerating more towards the center, it would start to spiral in. If it starts to get smaller, it could spiral out, okay? So there's lots of different things that can happen, but remember, we can change radial and tangential independently and then think about what happens to the velocity vectors as a result, okay? So in this case, this is a very simple case. All the acceleration vector is doing, pointing just in the radial direction and not changing, is changing the direction of the velocity vector. It doesn't change the speed, only the direction. So this is uniform circular motion, meaning that the speed stays the same and it only moves in a circle, and the change in direction is where is caused by the acceleration. So usually if you have something spinning in a circle, there's some force that has to be present to keep it going in a circle, okay? So I used to do this demo, but it's very messy. If you tie a donut to a string, you can do this at home, just make sure you're willing to clean it up. If you tie a donut to a string and you swing it around your head, what happens once the donut breaks? Does it keep going in a circle?
No.
No. What does it do? What kind of it flies outward. In what kind of trajectory, though? Curved line, straight line? Straight line, right? Because, as we know from Newton's laws, things that are moving are either moving in a straight line at the same speed forever, right? Or stopped unless you apply a force to them, okay? And we'll talk about that when we get to forces, but things like moving in straight lines, that's just how the universe works. There's not like a full explanation outside of that. But if things are moving in a circle, there has to be a force and there has to be an acceleration, okay? All right, so we're gonna try another problem. I'll give you guys a couple, this is a lot like what we just did. I'll give you about 5 minutes to work on it yourselves, and then we'll go over it together. And feel free to work together with the people around you.
Is the period always in seconds?
Sometimes it'll be given to you in other units, and
You don't have to convert it?
you don't have to convert it unless you need to plug it into something else.
Okay.
D squared over R.
That's an R-ish vector in the other direction. It's like X hat.
But this problem happened.
No, this has to go next.
Okay, so just do the D squared.
I don't know, there's an algebra. You did all the stuff right? The basics.
Okay. Did you get tangential acceleration? The first time having that frequency is divided by 2 pi. Yeah.
And then we got the acceleration.
Yeah, we don't need
Does exist in this one, but also it's the size of
All right. Oh, the camera lost me.
pretty fast physics.
Yeah.
That's almost like 60 feet.
Yeah. 4 times per. Yeah, that's pretty fast. Yeah. It's like it's fun. It's very safe. I'm trying to remember if I wrote this problem or if I got it from the book. We could actually like look at like a real Ferris wheel and see what the speeds are. This is probably in the range of normal, but like a little on the fast side. Yeah. Okay. So let's set this up. This is a lot like what we just did. We've just added acceleration into the mix. And remember, we have a couple of equations we want to remember before we get started, which is the speed, right? If it's uniform circular motion, obviously if it's not uniform, this doesn't work, is 2 pi r times frequency. And then we also know our acceleration, which I'll call radial acceleration, is speed squared over r. Okay, so reading through our problem, as we sometimes do, what do we have? Well, we have the radius, right, 9 meters, and we also have this 4 times per minute, which we can assume is a frequency. So we're given the radius and the frequency. So the radius, that's nice, it's already in meters, so that's 9.0 meters. Sorry, that's a terrible 9. Oh gosh. Let's try that again. Okay, and then the frequency is 4 times per minute. So what does that actually give us? How do we write that out? So we'd say 4 rotations over 1 minute, but of course we want things to be in seconds, so that's 1 minute over 60 seconds. 4 divided by 60 is going to be 1 over 15, and that's going to be in seconds, because remember, minutes goes away. So that's 1 over seconds, inverse seconds, or hertz. Okay? And it does sort of hurt that 1 over seconds is its own unit. Okay? So then if we want to calculate the speed, we just say 2 pi r times frequency, which we got from over here. And we can say 2 pi times 9 meters and 1 over 15 hertz. That's going to give us a speed of about 3.77 meters per second, okay? And then if we want the acceleration, we just know that that's speed squared over radius. So that's going to be 3.77 meters per second quantity squared over 9 meters. And that's going to give us 1.6 meters per second squared. So that's our radial acceleration. Now, someone did point out that there was an extra term when in the previous slide. So when we looked at the radial acceleration, it was written as a vector, which was v squared over r hat. What is the r hat in that situation? The r with the little arrow on top of it. What does that tell us? So what does x hat mean? Or y hat? Is it a value? What's the magnitude of it? So what did we use x hat and y hat for previously? It's been a while. Direction, right? This is a unit vector, right? So x hat was a vector of length 1 that points in the x direction. Y hat is a vector of length 1 that points in the y direction. What do you think r hat is? A vector of length 1 that points where? In the r direction. What does r? R is for radial, right? And radial means towards the center of the circle, because we defined this acceleration, this radial or centripetal acceleration, as always pointing towards the center of the circle. This is a vector. Remember, a vector includes magnitude and direction, so the direction is indicated by the. So, if you don't have a clicker, now's the time.
Thank you. Appreciate it.
Cool. It's better. Okay, so let's sort of break this down, and we'll use the chalkboard. It's a wild idea. So let's just calculate the accelerations, and then we'll compare them, okay? So remember, acceleration or radial acceleration or centripetal acceleration is just v squared over r. Okay, so we'll start with acceleration A, and that one's simple. It's v squared over r. If we do that for B, we now have 2 v squared over r, so that's going to give us 4 v squared over r. Okay? If you do this for C, that's going to be v squared over r, because remember, the direction doesn't matter, okay, because we're squaring it. So the acceleration is still the same. If we do this for D, you end up with v squared over 2r, which is the same as 1/2 v squared over r. And then last but not least, we get E, which is 2v squared over 2r. So that's going to give us 4 divided by 2, so that's 2v squared over r. So starting from largest to smallest, well, this one's going to be largest, right? This one's going to be smallest, so it will go B, E, A and C should be equal, and then D should be the smallest. All right, and that should give us answer, so B, E, this one, B. Cool. Any questions about that? All right, let's try another clicker question. Less mathy. Mostly B. Okay, please discuss. We'll vote again. Pretty much all the answers in the chat say B, so. All right, we agree that it's B. So I'm not going to go over that one, but it is directed towards the center of the circle. The answer is B. And so let's talk a little bit more defining. See, look, blue for position, green for velocity. So remember, just a review of all the stuff for uniform circular motion. Speed is 2 pi radius divided by the period, or 2 pi radius times the frequency. And centripetal acceleration is just speed squared over r. Centripetal acceleration is often written A sub c or A sub r for radial acceleration, right? So those all are the same thing. So we're going to define a couple more things, which is a new way of describing coordinates. Okay, so remember, regular position, just x, y coordinates. This is polar coordinates, right? So we can define circles a lot easier using polar coordinates, meaning the distance traveled, as long as you have the same radius on a circle, is really just described by the angle. Okay, this will hopefully give you flashbacks to the unit circle. The way that we've set up the unit circle, this is 0, and then you go around counterclockwise, and you can go all the way around to 180 or 2 pi. Okay, we've generally described these angles in radians, and we also have something called radial frequency, which tells you the angles per second. So let's try a review of sort of how the unit circle works. And note there are dots here, so there's a dot here, 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 and here. I think they're a little bit subtle. Should probably change the color, but let's try this clicker question. Okay. Chat says mostly C. This says mostly C. Please discuss quickly. We'll take about 30 seconds. Vote again. C. Yes, the answer is C, and we'll talk about why. So where's this dot? Yeah, so this would be 0, this is pi over 2, this would be pi, this is 3 pi over 2, and this is 2 pi or 0. Okay, so that we're just going counterclockwise around the circle, and all the way around the circle is 2 pi. Okay. So let's talk about how we use these coordinates to calculate things we've already calculated in x and y. So if we talk about motion along a straight line, distance between 2 points is our displacement, that's delta x. Remember, delta x is x final minus x initial. If you want the average velocity, or if it's a constant speed, you can do the change in position displacement over change in time, okay? If we're moving in a circle, we get something that looks like this, but instead of delta x, we're calculating delta theta. Now, a more direct translation of this would actually be the arc length, which is delta s. What is arc length? Just r times theta. So we just dropped the r because we're assuming we're going along a circle, the r is always the same. So it's a little bit different way of doing things, but it still gives you the same idea. And the nice thing about calling this delta theta, or the angular displacement, is that it now no longer matters where on the circle you are. You're always going to have the same change in angle, and you're always going to have the same speed. So this is our constant angular speed, right? Related to this, has slightly different units, right? Because this, what are the units of theta?
Degrees.
Yeah, degrees or radians. We're going to use radians. So this is going to be in radians per second, okay? So before we had this in meters per second, this is radians per second. If you want to go back to speed, you have to multiply it by r again, and that'll give you meters per second again, right? If you have a radius in meters, you can get meters per second. But the nice thing about this is, as you know, if you stand on something that's spinning, where are you moving the fastest? On the outside. So from a speed perspective, it matters where you are on the circle. But remember, if you have a spinning disk, this disk is all one object spinning together. Even though there's different speeds at different radii, it still represents sort of the same motion. So this gives you that information without having to know where on that object you are. Okay? So we call this angular speed. It's also sometimes called angular frequency because, as you can see, it's actually more of a frequency than a speed because it doesn't have a distance in it. Specifically, it only has angle. It's a little bit complicated, but it's a new variable that we're dealing with. So now if you're translating back and forth between our traditional coordinates and our new circular coordinates, we have angular displacement, which is an angle, and now we have angular speed, which is omega. It's like a fancy Greek W, okay? Big omega, look here, look over here. Big omega looks like this, like an ohm, okay? Little omega looks like a W. I don't know. Greeks were doing this whole alphabet thing before we were, so maybe they knew what they were doing. All right, let's try a clicker question. Okay. Mostly C. Okay, please discuss. We'll vote again. Better. So, yeah, wait, we're going to actually do that now. That's what we usually do. So, the answer is C. Here's the thing. The centripetal acceleration, remember we talked about this briefly, and we'll talk about it in a lot more detail in the next couple chapters, but if you have an acceleration, that's because there's a force, okay? And so when we talk about Newton's laws, the first law says that bodies in motion stay in motion, bodies at rest stay at rest. What that really means is if something's moving, it will keep moving in a straight line at the same speed forever unless it's acted upon by a force. Okay, so things like to move in straight lines or not at all, those are the only options. So what's happening here, this ball goes around the circle, okay? As it's moving along the circle, there is a force pushing it in the circular direction. What is that force? Yeah, this actual track is like the force pressing on it. It's actually a normal force, which is the force that keeps you from falling through the ground too. So it's if you want to break it down, it's a bunch of electromagnetic forces of molecules that are stuck together. But essentially, if the ball is rolling along this track, the track pushes it inwards at all points so it doesn't turn. The ball wants to go straight, but it keeps hitting something and then it turns, and that's the centripetal acceleration. Once the track ends, though, there's nothing that points it into the center of the circle. So at each point, if you look at the velocity, just like we did in the circles in the earlier slides, it's tangential to the circle. So as soon as you take away the force, now it has nothing curving it. It has to go in a straight line. okay? Things always go in a straight line unless there's a force. So once the force is gone, straight line, okay? And if you really don't believe this, you just take this, you make one of these, you take your slow-mo camera and you put a ball through it, it will do this.
So like, let's say you're going this way, and then something ends. There's no way you're just gonna, out of nowhere, just go left. You know what I mean?
So it's, yeah, but it'll shoot straight up, right? If it's at an angle, then it will then have the parabolic arc of free fall motion. So you can try this at home. All you have to do is build a circular track that points exactly up at the end. No big deal. If you have access to the 3D printers, it's actually pretty easy. But yeah, just ask Keenan. So, okay. Yeah. So this brings us back to speed, angular speed, non-uniform, okay? And that means these are derivatives. So what's the angular speed going to look like? Remember, now instead of x, we have theta. So if you want angular speed, what is that? It's not dx dt, just d theta dt, okay? If we have speed, we can say that's 2 pi r times frequency. If we want angular speed, it's just 2 pi times frequency, okay? So remember, angular speed is radians per second. Frequency is 1/seconds. 2 pi is in radians, so you'll get radians per second. The way that you go back and forth between speed and angular speed is just multiplying by the radius, okay? So if you have angular speed and you want regular speed, just multiply by the radius. Okay, so that's the distance you are from the center of whatever is spinning. All right? And remember, angular speed is special. Part of the way we designed it is so it does not depend on radius, okay? Once again, what are the units of angular speed? Radians per second, okay? All right, we're gonna try another problem where we get to do fun unit conversions. I hope you like dividing things by 60. So I'll give you guys a couple seconds maybe a minute to work on this, but then we'll go over it together. You have about the amount of time it takes for me to switch screens. This one's not super complex. So we have a disk in a hard drive in a desktop computer, which so we still have some of these. A lot of them are solid state now, which is not disk based, but whatever. So all these dated spinning questions. We have it rotating at 7,200 RPM. That's rotations or revolutions per minute. The disk has a diameter of 5.1 inches, which is 13 centimeters, and we want to know the angular speed of the disk. So we're going to start with the frequency, and what do we have to do with the frequency?
RPMs by 60.
Yeah, so 7,200 rotations per minute. We want this in seconds, so 1 minute is equal to 60 seconds. That's going to give us 120 inverse seconds, which we call hertz, because somebody was once named Hertz. Okay. And then if we want the angular speed, which is also sometimes called the angular frequency, all we do is multiply that by 2 pi. So that's going to be 2 pi times 120 hertz, which is going to give us 750 radians per second. So that's our answer. Yeah, radians per second. Any questions about that? Okay. Cool. Let's then move on to, so here's, remember for centripetal acceleration, this is just rewriting our centripetal acceleration to be v squared, right? Speed squared over r. You can also write it as omega squared r. There's just a little bit of algebra here. So remember, we know that, how are these related? Well, this relationship happens here. So if you just take v squared over r and you plug this in, you end up with omega squared r squared over r, which is omega squared r. Okay, so really just saying the same thing. All it does is give you a couple different options to get your centripetal acceleration. Remember, this can also be written with a c or with an r. And this is just the magnitude. If you want to write this as a vector, what do you have to add back in? Yeah, so you'd have to say, oh, look, r hat. Okay. Okay. So let's try another problem. This one starts off with the same thing we just did, but then adds a couple things. So if you just followed along with that one, you can skip straight to the finding the acceleration from the angular speed part. Okay, anybody need more time to think about this? This one's some nice plug and chug sort of questions. Always fun in physics. Okay, how do we calculate speed? We already calculated angular speed, so yeah, we just plug in the radius. So if we want to calculate the regular speed, we just take omega, which we calculated, and multiply it by the radius. In this case, we know it's not even asking for the speed at the edge, it's asking for it at a specific distance. So this is 6 centimeters from the axle, which is not quite the edge. The edge would be 6.5 centimeters from the axle. So we say, okay, we have 750 radians per second. And then if if it's 6 centimeters, that's our radius, so that's going to be 0.06 meters. And that's going to give us 45 meters per second. Now, here's a fun thing. What happened to the radians? Yeah, that's a good question. It turns out radians are only kind of a unit, so we use them as a placeholder, so we know it's not just 1/seconds, but once we add meters back in, we just get rid of them because it's confusing, but that's how we do it, okay? So radians just go away if you multiply them by meters. Sorry. Okay, so here's our speed. I'm going to get rid of this circle here. And then the last thing we want to do is we want to calculate the centripetal acceleration. So we'll say we'll call this A sub C for centripetal. That's going to be omega squared R, or you could, since we have the speed, you could do speed squared over R. Both of those are fine, but they'll give you the same answer. So we say 750 radians per second, and then that's going to be squared, and then this is 0.06 meters. Plug all that in, you get about 34,000 meters per second squared, and once again the radians squared has just vanished, but that's kosher in this case. So here's your acceleration. So now we have speed and we have acceleration. All right, and that is a pretty, thing is going at a nice clip. All right, cool. Moving back to desktop 2. So just to review, if we're going from linear to angular motion, this is really just a table for your reference. It's in the notes. But position, we just make theta instead of x. Velocity is going to be the derivative of theta with respect to t. And then that gives us acceleration, which we represent with an alpha. So this is angular acceleration, which is the time derivative of angular speed. Okay? Cool. So we've been talking about speed being constant, meaning that acceleration is really just the one that points it towards the center of the circle. But what if we're speeding up or slowing down? What if acceleration is not constant, right? What if we're doing this? So if we are actually speeding up or slowing down, you can see the velocity vectors get more complicated, right? They're getting longer as we go along, so that indicates that we're going faster. That also means that all the centripetal accelerations get bigger. Why are they getting bigger? How is centripetal acceleration related to speed? Well, it's speed squared over the radius. The radius isn't changing, but as the speed gets bigger, that means the acceleration towards the center of the circle also has to get bigger. So it takes more force to keep it moving towards the center. But now we have something we call the tangential acceleration. You can see here, the tangential acceleration is constant, right? It's tangent to the circle, and that's what causes the velocity vectors to get longer. Okay, so these are all your tangential accelerations. Because we now have centripetal and tangential accelerations, if we want to find the actual just acceleration vector, we can do the thing where if we have two perpendicular vectors, we can take the resultant vector. We can add them together. And so if you wanted to see the actual acceleration vectors, they look something like this. Okay? So that's just your standard acceleration vector. So essentially, a lot of stuff is happening here. So as speed increases, the acceleration vectors that point towards the center have to increase because they're related to the speed. Also, in order for the speed to increase, that means there's acceleration vectors that go in the tangential direction that cause the speed to increase. Okay? So you have both your radial and tangential acceleration vectors changing in this case, when before we just had a constant radial acceleration vector. Okay, so if you want to describe this in terms of our angular coordinates, you can describe acceleration as dw dt, and this is always related to, remember, because this only describes sort of the motion around the circle, this one's always going to be related to the tangential acceleration. Just like before, when we were talking about moving back and forth between omega and v, that's the tangential v. The only reason we didn't write that is because we haven't seen any cases where the velocity points in the radial direction, but if it's tangent to the circle, the direction is tangential. Because remember, we've created this new coordinate system where everything is either radial or tangential because those are our new perpendicular coordinates, which is weird because when you think about it as a coordinate system, it's not static, right? The coordinate system is actually moving around the circle with the object and turning. Kind of weird to think about, but really it's still just sort of like an XY coordinate system, but now it's moving with the object, okay? Coordinate systems are really just what we make them. Okay, so we're going to try using this, and I'll give you guys a couple minutes to set this up, although we're running a little bit low on time, so I'm going to get started on it in a couple minutes, but at least look over the problem, try to write down the variables you're going to use, and then we'll reconvene and we'll do it together. It's a very bad drawing of a drill. Okay, so if you start a drill, what is it doing before you turn it on? Nothing. So what would your initial angular speed be? 0. So we know that we're going to start from 0. So that's 0 radians per second. But then we find that it's going to go in 2.5 seconds. It's going to go up to 24. Oh, sorry. Can't see what I'm doing. Cool. You can't see my terrible drill drawing. Now you can. All right. So, all right. Let's start. We're good. So that's our initial speed. That's in radians per second. But we can calculate our final angular speed. So this is going to be 2.5 seconds in 2,400 rotations per minute. So we want 2 pi times our frequency, right? Our frequency is 2,400 rotations per minute, so 2 pi times 2,400 rotations per minute. Once again, we need 1 minute, 60 seconds. This is going to give us 250 radians per second, okay? So this is our initial and final speeds. If we assume, which this question doesn't say, but I don't know any other way you would do this, that this is going to be a constant angular acceleration, you can define your angular acceleration as delta omega over delta t. So that would be omega final minus omega initial over this time, delta t. Okay, so that's going to be 250 radians per second over 2.5 seconds. Anyone want to do that in their head? Yes, 100, thank you. 100 radians per second squared. So this is our angular acceleration, okay? We'll make it orange for acceleration. It's 100 radians per second squared, and that's part A. Okay? For part B, we want to know how many revolutions does it make as it reaches top speed. So over the time of 0 to 2.5 seconds. Yes, do you have a question?
Isn't it 10?
So 100 divided by 1.
250?
It's 2.5, not 25.
Oh, okay.
Yeah.
Sorry.
I mean, maybe the dot's not visible. But anyway, don't worry about it. Orders of magnitude, what are they among friends, really? So if I owe you $100, I'll just give you 10. It's fine. No, it's fine. It's a good question. So the other thing is, how many revolutions? How do we calculate revolutions? What variable would that be? Kind of. So we have acceleration. So what we would normally worry about are speed and distance. So which of those things seems closest to revolutions? Distance, right? And we can get our distance in radians, okay? And if we get a distance in radians, how do we decide how many revolutions that is? Well, how many radians is one revolution? Radians. How many radians are in one whole circle? Pi, something with a pi in it. 2 pi. Yes, okay? So if we calculate how many radians we go through in this time, then we can calculate how many revolutions by dividing it by 2 pi. Okay, so we're going to go back to a kinematics equation. Because remember, everything that we did, x, velocity, acceleration, position, velocity, acceleration, we have translated now into angular stuff. So we can say theta final is equal to theta initial plus omega initial t, right? Plus 1/2 alpha t squared. All right, everybody okay with that? We can rewrite this to be a little nicer, so we'll call that delta theta is equal to omega initial t plus 1/2 alpha t squared. What do we know about our omega initial? Well, it's 0, so we can get rid of this term, okay? So now we have, oh, geez. That's not good. Now we're solving for delta theta, and that's going to be 1/2 alpha t squared. Well, we know all that. 1/2, this is 100 radians over second squared, and then we have 2.5 seconds squared. So we plug all that stuff in, and that gives us 312.5 radians. Okay? What do we do with this? Yeah, so we have 312.5 radians divided by 2 pi, which we will call radians per revolution. Okay, so radians per one time around a circle. Circle stuff gets crazy. So do that. Turns out you divide this, you get 50, because I picked all these numbers to be really nice. So 50 revolutions until you get up to speed. Okay? All right, that is all we've got for today. I will see you guys on Thursday, and we'll be doing a lab where we shoot stuff out of, like, spring-loaded guns. It'll be fun.